Hello, and welcome to another Algebra 1 lesson. This is lesson 9.1. Our objective, use properties of radicals to simplify expressions. Let's start with a few warm-ups. What's the square root of 16? 4. What's the square root of 64? 8. Square root of 36? 6. Now remember, it's because 4 times 4, or 4 squared, is 16. It's what number squared gives you that number. These next few are a little bit harder. So what we can do with this is 400 is the same as 4 times 100. What's the square root of 4? And what's the square root of 100? And then we can do 2 times 10. 20. How about 3,600? Okay, we can see that as 36 and 100. And do the square root of each of them separately. Square root of 36 is 6. Square root of 100, well, 10 times 10 is 100, so that's 10. So our answer is 60. Now, this works. We can break it up this way, but we can also break it down into prime factors. 225 is divisible by 25. 25 goes into 225 how many times? So I'm thinking quarters. How many quarters would be $2.25? 4, 8, one more is 9. Okay, and then 25 is 5 times 5. And 9 is 3 times 3. So we can now look at this as the square root of 3 times 3 times 5 times 5. And when we find the square root, we can pop out the pairs. Every time we have a pair of the same factor, we get 1 on the outside. Because 3 times 3 is 9, the square root of 9 is 3. So 2 3's underneath the radical become 1 3 on the outside. 5 times 5 is 25, so this pair of 5s becomes 1 5 on the outside. Final answer, 3 times 5 is 15. So when simplifying radicals, some of them we may have memorized. Some of them we may see it as 2 numbers we already know the square roots of, like 4 and 100 or 36 and 100. Or we can break it down into prime factors and pop out the pairs. Investigating operations with radicals. For each operation with square roots, compare the results obtained using the 2 indicated orders of operations. What can you conclude? Square roots and addition. Square root of 36. Square root of 64. What number times itself gives you 64? 8. And then 6 plus 8 is 14. So is the square root of 36 plus the square root of 64 equal to the square root of 36 plus 64? Well, this works as a grouping symbol. The radical sign becomes a grouping symbol. So this is all grouped together. 36 plus 64, add those up. That's 100. What's the square root of 100? 10. So these are not equal to each other. So when we have addition inside a square root symbol, we cannot break it apart into the square root of 2 different things and then add. It will not give us the same answer. So in general, the square root of A plus the square root of B is not equal to the square root of A plus B. So no, it is not. Did not give us the same answer. Okay, let's look at multiplication. Square root of 4. Square root of 4 is 2. Square root of 9 is 3. 2 times 3 is 6. Okay, what's 4 times 9? 36. And the square root of 36? These are equal. So it works with multiplication, but it did not work with addition. So in general, the square root of a times the square root of b is equal to the square root of a times b. It works for multiplication, but it does not work for addition. So our reasoning is the example that we have. See the example. Here's some properties of radicals. A radical expression is an expression that contains a radical, a square root symbol. An expression involving a radical with index n is in the simplest form when these conditions are met. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions. No radicals appear in the denominator. We cannot leave a radical in the denominator. Things like the square root of 3 are irrational numbers, and we are not allowed to leave an irrational number in a denominator. Square root of 3 is irrational because it's a decimal that never ends and never repeats. You can use the property below to simplify radical expressions involving square roots. The square root of a times b is equal to the square root of a times the square root of b. And then here's a numerical example. Square root of 9 times 5 is the same as the square root of 9 times the square root of 5. We do not know the exact square root of 5, but we do know the square root of 9 is 3. So the square root of 9 times 5 is equal to 3 times the square root of 5, also read 3 rad 5. This is simplest form for this expression. Let's simplify 108. I don't know the exact square root of 108, so I'm going to break it down into prime numbers. Find my prime factorization. So it ends in an even number, so I know it's divisible by 2. Divide this number by 2, what do we get? 54, good. So now let's break that down. I'm running out of room over here. So this is 108. 2 times 54. 54 is 2 times 27. 27, well, that's 9 times 3. Keep going. Let's write our prime factors in order. We have a 2 and a 2. Just the prime numbers. Don't use any of the numbers in the middle. Just the ends of the branches. 3, 3, and 3. So we have 2 times 2, and then we have 3 3s. For every pair of like factors, 1 pops out. So this pair of 2's becomes 1 2 on the outside. We have a pair of 3's that becomes 1 3 on the outside. Pairs go out, singles stay in. Pairs go out, pairs pop out, singles stay in. So this 3 has to stay inside the radical. If you have more than one number outside or more than one number inside, you can multiply them together for your final answer. 2 times 3 is 6. Our final answer, our simplified form of the square root of 108 is 6 rad 3. Right, let's try the next one. 9 and x cubed. So we can do these in separate pieces. X cubed. Let's write it this way. You don't have to, but I think it's helpful, at least for a little while. The square root of 9 is 3, because 9 is a pair of 3s, so we have a pair, so 1 pops out. We have a pair of x's, so we get an x on the outside, and then singles stay in. So that x that doesn't have an identical factor has to stay in the radical. This is our final answer. 3x times the square root of x. That's the simplified form of the square root of 9x cubed. And that's example 1. Quotient property of square roots. The square root of a quotient equals the quotient of the square roots of the numerator and denominator. So take a look. The square root of 3/4 can be broken up into two radicals, one with the numerator and one on the denominator. And we know the square root of 4 is 2. So the square root of 3/4 is equal to rad 3 over 2. In general, square root of a over b is equal to the square root of a over the square root of b, as long as a and b are positive numbers and b cannot be 0, because we can't divide by 0. All right, so let's break it apart. Square root of 15, square root of 64. Okay, so I'm thinking factor trees, pop out my pairs. 15 is a 3 times 5, no pairs there. So that just stays the square root of 15. What about 64? Do you remember the square root of 64? If you do, great, write it down. And it'll be outside the radical. If you don't, well, then we can break it down. 64 is 2 times, divide this 64 by 2, we get 32. That's an even number, so I know I can divide it again. 2 goes into 32 16 times. 16 is 4 and 4. Oh my goodness. Keeps going. And then we get a 2 and a 2 for that 4. And a 2 and a 2 for this 4. So how many 2's do we have? 1, 2, 3, 4, 5, 6 2's. For every pair on the inside, we get 1 on the outside. So here's a pair of 2's. We get a 2 on the outside. We get another one for this pair, and another one for this pair. Oh, everything popped out. 2 times 2 is 4. 4 times another 2 is 8. Did you remember that the square root of 64 was 8? Save you a lot of time if you did, because 8 times itself gives you 64. 8 squared is 64. Square root of 64 is 8. All right, that is our final answer for that one. Rad 15 over 8. All right, next one. Square root of 81. Don't make me break it down. Do you remember that one? What number times itself gives you 81? 9, yes. And then x squared is just an x times an x, so we have a pair of x's, so the square root of x squared is just x. Squares and square roots undo each other. And there's our final answer. And that's example 2. Example 3, use properties of cube roots. Well, with square roots, we were popping out sets of 2, popping out pairs. Well, now it's a cube root, so we're looking for sets of 3. Let's break down our 128. But notice these are all a cube root. This little 3 right here is called our index. And whatever our index is, that's the size of the set of things we need to pop them out. So 128 is 2 times, 2 goes into 12 6 times, 2 goes into 8 4 times, so that's 64. Oh, we know 64. That's 8 times 8. 4 and 2. 4 and 2. 2 and 2. 2 and 2. Okay. The cube root of a negative is a negative. The cube root of a positive is a positive. Let's see, how many 2's do we have? We have 7 2's. Let's write them all out the long way. And because we're doing a cube root, we're going to look for sets of 3. So these 3 2's become 1 2 on the outside. We have another set of 3 2's, so those 3 2's become another 2 on the outside. This one stays in, and it's a cube root of 2. Our answer is also negative. 2 times 2 is 4, so negative 4 cube root of 2. Now, one way you can help check your answer, it won't check it exactly, but if you have a calculator handy, and you can do the square root, or sorry, cube root of negative 128 and hit enter, and you do negative 4 times the cube root of 2 and hit enter, and they both give you the exact same decimal answer, then at least you know your answer is equivalent to the starting answer, the starting problem. All right, B. Cube root of 125. Well, let's make a list for a minute. 1 cubed is 1, so the cube root of 1 is 1. 2 cubed is 8. I want you to start to see the pattern. Four cubed is 64, so the cube root of 64 is 4. What about 5? 5 cubed. 5 times 5 is 25. Times another 5? 125. So the cube root of 125 is 5. So if you can memorize some of the numbers cubed, then you can go backwards and do the cube roots a little easier, a little faster. Cube root of 125 is 5. So I did all that so you would think ahead and be able to do some of these easier. Like here's an 8, here's a 27. It'll help with some of these. Okay, and then a cube root of x to the 7th. X to the 7th. 1, 2, 3, 4, 5, 6, 7. How many sets of 3 do we have? There's 1. There's another set of 3. So it's another x that pops out, and this one has to stay inside the radical. So our final answer, 5x times x is x squared. 5x squared times the cube root of x. There's our final answer. Okay, 216. Makes me want to go back to my list. What's 6 cubed? 6 times 6 is 36. What's 36 times 6? 216. That means that the cube root of 216 will be 6. So cube root of y over the cube root of 216, which is 6. That's our answer. And the next one, what's a cube root? Let's separate our numerator and denominator first. 8 x to the 4th. I'm going to write this out. And then 27 y cubed. All right. Cube root of 8 is 2. Cube root of x times x times x times x, we get 1x on the outside, 1 left on the inside, so that's 2x cube root of x. And our denominator, what's the cube root of 27? 3. And we have 3y, so that pops out. No radical left in the denominator. There we go. We just simplified 4 cube root problems. Rationalizing the denominator. When a radical is in the denominator of a fraction, you can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. This process is called rationalizing the denominator. So when we have an expression like this with a radical in the denominator, we are going to multiply the numerator and denominator by what's in the denominator, the square root of 3 times n. When we do that, it creates a pair. So I'm going to change this to a times sign. We're multiplying by rad 3n over rad 3n. So anything divided by itself is just equal to 1, some form of the number 1. So now we have a pair of 3's, the 3 pops out. We have a pair of n's, the n pops out. And here, both of these are inside the radical, so we will go ahead and multiply them together and put it inside the radical. There's our answer. All right, the next one, 2 over the cube root of n. This one's a cube root, so we don't need pairs. Instead, we need sets of 3. So 9 is 3 times 3. So we already have 2 3's, but we need a third 3 for it to pop out because we need sets of 3. So we are going to multiply by the cube root of 3, and whatever we do on the bottom, we'll do that because it gives us 1, 2, 3 of them, so the 3 can pop out. Whatever we multiply the bottom by, we must multiply the top by. So this is what we're doing. And then multiplying this numerator together, the 2 is outside a radical and this 3 is inside the radical. So when one number is inside and one number is outside, we do not actually multiply the numbers. So we're not going to get a 6. We're just going to place them next to each other because that means multiplication. This means 2 times the cube root of 3. So 2 times the cube root of 3 over 3. That is our final answer. So that's called rationalizing the denominator. It is making sure that you are not leaving a radical in the denominator. Because things like the square root of 3, that's an irrational number, and we want it to be a regular 3. We want it to be a rational number. So rationalizing the denominator means getting the irrational numbers out of the denominator. And all we did was multiply by a special form of the number 1. Conjugates. The binomials a rad b plus c rad d and a rad b minus c rad d, where a, b, c, and d are rational numbers, are called conjugates. You can use conjugates to simplify radical expressions that contain a sum or difference. Rationalize the denominator using conjugates. So the conjugate of 2 minus rad 3, look here, if we had radicals and we had a plus, its conjugate is going to be the same numbers, but instead with a minus. So we are going to multiply, this one has a minus, so this one needs a plus. We can multiply the denominator by anything we want, as long as if we multiply the denominator by it, we also multiply the numerator by the same thing. Because then all we're doing is multiplying by a form of the number 1. All right, so here we go. 7 times 2. 7 times rad 3. All over. Okay, be careful with this one. We have a binomial times a binomial, so we're going to do 4 multiplications. 1, 2, we're going to do those. 2 times both of these, and then we'll do negative rad 3 times both of these. All right, 2 times 2. 2 times rad 3. So in a minute, you're going to see how this works to get rid of the radicals. These conjugates are like magic. It's like magic. It's going to magically make all the radicals leave the denominator. Doesn't look very good so far, so let's keep going. Now, when we multiply negative rad 3 times 2, that's negative 2 rad 3, or minus. And then negative rad 3 times positive rad 3 is negative rad 9, because 3 times 3 is 9. Well, let's simplify this. Numerator is fine the way it is. 4 plus 2 rad 3 minus 2 rad 3. Combine like terms. 2 rad 3 minus 2 rad 3. That adds to 0. And what is the square root of 9? 3. So we have 4 minus 3. What's 4 minus 3? Just 1. But wait, there's only a 1 in the denominator, so we don't even need it. 14 plus 7 rad 3. Final answer. No longer do we have an irrational number in our denominator. We rationalize the denominator, and we use conjugates to do it. All right, we're going to jump to example 8. I may or may not come back to example 6 and 7. Let's see how long this takes. Performing operations with radicals. Radicals with the same index and radicand are called like radicals. You can add and subtract like radicals the same way you combine like terms by using distributive property. Okay, they have to have the same index and the same radicand, the number inside the radical. So 5 rad 7 plus rad 11 minus 8 rad 7. So it's like 5 apples plus 1 banana minus 8 apples. We're looking for the like terms. The rad 7s are the like terms. So 5 apples minus 8 apples. What's 5 apples minus 8 apples? Negative 3 apples, but they're not apples. They're rad 7s. And then this one has a rad 11. It is not a like term, so we just include it in the answer. This is our simplified form of the first expression. Let's look at the next one. 10 rad 5 plus rad 20. Well, these are not looking like terms right now. Rad 5 and a rad 20, the radicands do not match, but 20 is 4 times 5, and 4 is a pair of 2's. So we get a 2 that pops out and a 5 that stays in. Now look at it. 10 rad 5 plus 2 rad 5. Well, 10 of these plus 2 more of these is 12 of these. So 10 rad 5 plus 2 rad 5 is 12 rad 5. All right, the next one. We have a cube root of x and a cube root of x. So these match. So we have 6 of these. Let's call them pineapples. 6 pineapples plus 2 pineapples is, 6 plus 2 is 8 pineapples. But they're not pineapples, they're cube root of x. That's all we have to do for that one. So be careful when we are multiplying radicals. We can multiply any radicals together we want. But when we're adding and subtracting, we have to have like radicals. Just like adding like terms. If you have like a 3x and a 5y, you can multiply them all day long, but you can't add 3x and 5y. You would have to just write out 3x plus 5y, like we did with this rad 11. We couldn't combine it with the other stuff. Right, so watch for those like terms. Multiplying radicals. All right, multiply, multiply. Rad 5 times rad 3 is rad 15. Rad 5 times rad 75, I don't know what that is. And you know what? I'm not even going to figure it out because I'm going to break it down anyway. 75 is 25 times 3. 25 is 5 times 5. So we have rad 15 minus square root of 3 times 5 times 5 times another 5. So we have a 3 and 3 5s. It is a square root. Okay, I just double checked to make sure it wasn't a cube root. So we are popping out pairs. Square roots have an invisible little index right here of a 2. We're looking for pairs. So the 5 pops out. 5 pops out. 3 times 5 stays inside, but multiplying back together. So that's 3 times 5 is 15. So now we have like terms because this is a rad 15 and this is a negative 5 rad 15. So I'm going to put in a 1. 1 of these minus 5 of these. 1 minus 5 is negative 4, and we were adding or combining rad 15s. So negative 4 rad 15 for our final answer. That's example 9, multiplying radicals. What does rationalize a denominator mean? Okay, let's pull it apart. What's a denominator? That's the bottom part of the fraction. And what's a rational number? Well, numbers like 2, 3, 4, those are all rational numbers. But things like square root of 3 are not rational numbers. So to rationalize a denominator means make sure you only have rational numbers in your denominator. So we could say, let's see, how could we say that? There we go. Get the radicals out of the denominator. That's what it means. When we see rationalize the denominator, it means we can't leave those irrational numbers in there. We got to get the radicals out. Get the radicals out of the denominator. Once you've done that, then make sure you've simplified. Look at the top and the bottom, the numerator and denominator, see if there's any more simplifying to do. But always make sure you rationalize the denominator. Do not leave a radical on the bottom. All right, this is what we need for Big Ideas, assignment 9.1. We're in chapter 9. All right, good job, guys. Thanks for watching. Have a great day.